So hello everyone and welcome to today's webinar. Today's webinar is titled Patient-Specific Spine Analytics. My name is Christopher Iverson and I will be the host of this webinar. I work here as Anybody Technology as the sales executive and I'll host this webinar throughout the day. So to begin with, I'll just give you a short outline to what we are going to hear today. So at first we will have a short introduction of all the speakers. And then we will have a presentation, and it will be a joint presentation between Academic Medical and Anybody Technology. And we will hear from Chief Medical Officer from Academic Medical, Dr. Isidor Lieberman, the Vice President of Research and Development from Academic Medical, Kobe Blanc, and the Senior Algorithm Engineer from Academic Medical, Samuel Shannon. And then we have a Senior Consultant from Anybody Technology, Pavel Galibarov, from our side as well. So first of all, I would like to point your attention to the control panel. The control panel appears on the right side of your screen, and you are very welcome to submit questions and comments via the question panel throughout the session. We will do our best to answer all of the questions in the end of this webinar during the Q&A session, but in case we get a lot of questions, we will try to do so and answer them by email within a reasonable time. So please feel free to submit your questions just as we go. And with that said, I will hand over the presenter role to Dr. Lieberman. Just 1 second.
Good morning, everybody. Thank you for being with us. It's an absolute privilege to have this opportunity to be able to present the collaborative efforts between Agada Medical and Anybody Technologies. We've been working at this for a number of years now, and it's been very, very fruitful lately. And it's just exciting and quite frankly intimidating knowing some of the people in the audience to be able to present this to you. This is who we are today on the talk representing Agada Medical. Myself, Izzy Lieberman. I'm an orthopedic and spine surgeon. I have been in this field now for 32 years. I've worked at the University of Toronto, the Cleveland Clinic, and now I'm at the Texas Back Institute. And I've been involved in a number of startup companies, as well as involved in a number of clinical research studies and working away in spine as a surgeon. With us, we have Kobe Blanc, who is our VP of Research and Development. Kobe has over 20 years of experience with mechanical engineering in medical devices, imaging, active implant manufacturing. He's been critical to our growth at Agada, and his guidance has gone without any particular losses to the commitment that he's brought to the organization. Also with us is Mr. Samuel Shannon, who is our Senior Algorithm Engineer. I'm very proud to be associated, and to work for Samuel, for Shmulik, as we refer to him. He really has been the heart and soul behind the algorithm, the work, and doing the stuff to get us where we are, and what I presume is going to be very exciting to all of you to see how we've been able to advance this. So this is the problem that we are trying to tackle. Nearly a third of spinal surgeries worldwide that are performed today fail. They don't result in the outcome that the patient expects or the surgeon expects. As good as we think we are as surgeons, we are still not good enough. Right now in the United States, the spine surgery market is a $10 billion market. The majority of it is divided between spinal deformity surgery and spinal degenerative surgery, which accounts for approximately 600,000 surgeries a year. But when you look at the number, if a third of those fail, you're looking at 200,000 individuals that need a revision surgery. And the cost of that revision surgery to the US healthcare system, to society, to the insurance companies as it stands right now is $5.6 billion. Now, the need is the ability to predict the forces on the spine and the clinical outcomes. If you look at the spine continuum of care, if you look at medicine in general, there's been a lot of discussion lately about artificial intelligence, about preoperative planning, about 3D printing and patient-specific implants. The problem is we have not had the tools to fully analyze the biomechanics of the spine. And we make the analogy of architects and engineers. The architect can design the most elaborate building, but the architect does not have the skill, the expertise, or the tools to figure out how to keep that building standing. So in combination with Anybody Technologies and Agada, what we are doing is applying science to the art and providing the surgeons with the tools to analyze the forces and to ultimately predict the clinical outcome so that we can ensure the most appropriate outcome for our patients. And the way we do that is with our software platform that we've called the Spine Oracle. By calculating the forces along the full length of the patient's spine, we can take the art of surgery from descriptive analytics to the science of surgery with prescriptive artificial intelligence, providing the surgeons with the most appropriate, least invasive surgical strategy to ensure an optimal outcome. The components of the Spine Oracle include our human modeling software, our biomechanical simulation software, and the integrated artificial intelligence at multiple steps throughout the procedure. So this is how we've combined forces with Anybody Technologies and the workflow of the Spine Oracle software. We take the patient's imaging studies and their anthropometric data. We create a patient-specific digital twin from that data. This is a volumetric segmentation, including muscle and ligaments for the dynamic force analysis. And Pavel and Shmulik are going to elaborate more on that. We then transform the patient-specific digital twin into our dynamic force analysis model. We run the model through the patient's native state, so we understand what the preoperative biomechanics are along the entire length of the spine. We then perform multiple different dynamic analyses comparing surgical strategies, a one-level fusion, a two-level fusion, a disc replacement, a fusion to the pelvis. And we can then compare those surgical strategies, providing the surgeon with the decision support mechanism to choose what he or she feels is the most appropriate strategy for that patient. As we gather data, as we get patients, as we understand the implants, the anthropometric data, the various other variables that we have to deal with, and amass that information, we then begin with our artificial intelligence, the machine learning, the predictive analytics, and in summary, the big data analysis to create that neural network and build those clusters to figure out what's going to happen to the next patient that comes along that has similar anthropometric data, similar pathology, and is operated by surgeon X at hospital Y with implant Z. And that's how we're going to optimize the surgical solution to prevent a poor outcome. Now, there's a little bit of selfishness to this. I know at some point in my life, I'm probably going to need spine surgery. So I want to make sure that whoever is operating on me knows exactly what's going on from a biomechanical perspective, because biomechanics is what determines function and outcome in the musculoskeletal realm. Now, this is our case demonstration. This was really our proof of concept. This is a 77-year young female On the far left, you can see clearly she's leaning to the left, she's pitched forward, she's got terrible alignment, and she's got terrible compression of the nerves. So she's got stenosis with pain radiating down the legs, difficulty with her mobility. Using the commonly available preoperative planning software, I planned a surgery on her, and we were able to achieve all the parameters that we set out to achieve. The shortcoming was this was based on two-dimensional analysis. This was not based on biomechanics. Now everybody's happy. We got all the numbers exactly where they need to be, her lordosis, her sagittal plane. We've got her anchored to the pelvis. But she comes back to me 6 months later with 2 broken rods at the L5-S1 junction. This should not have happened. This was not meant to happen. If you look at the picture on the far right, we then analyzed this case in a retrospective fashion using the spine oracle. And the spine oracle predicted the increased rod stresses at that L5-S1 junction. And here is the graphical representation of that. The red line is the yield point of the titanium rod. If you look at every other level along the length of the spine, the rod does not see the stresses anywhere near its yield point. The rod will not break. At L5-S1, you see almost 2.5 times the stress of that rod at the yield point. Now, if I knew that as a surgeon before the operation, I could have done something different. I could have avoided the revision surgery for her. And there's dozens of things that I could have done, but I didn't have the tools to fully analyze that at the time and optimize her outcome. Now, it's not just hardware failure. There are multiple other unmet clinical needs. We now have the ability to look at the proximal junctional issues, look at the stresses in the upper instrumented vertebrae or the upper instrumented vertebrae +1. We can look at the implant bone interface and analyze the stresses there. I can preoperatively determine, do I need to augment those vertebral bodies with cement prior to putting the screws in? We can also look at the issues of adjacent level degeneration. There's a lot of debate as to the etiology of adjacent segment degeneration. But now with a 1-level or 2-level fusion using the spine oracle as a decision support software, we can analyze the intradiscal shear forces at the levels above and below. We can look at the facet contact forces at the level above and below. And we can design the surgical intervention to optimize those forces, to eliminate the amplification of forces above and below, which we intuitively feel predisposes that individual to the adjacent segment deterioration. So with that, I'm going to hand it over to Shmulik to talk about our automatic spine segmentation module.
Hello, I am Samuel from Agada Medical. I'm going to talk how we prepare the patient-specific model for the Anybody software. So during our research, we have developed automatic segmentation tools for segmentation of the spine and the pelvic, utilizing a deep learning approach. The segmentation tools is highly efficient for preoperative CT scans with cracked spine, as well as for postoperative CT scans or revision CT scans with implants that can sometimes produce a noise. The segmentation tools can identify the vertebral body, the end plates, the pedicles, and the facet joint. achieving a dice coefficient of 0.96. Research, we have developed a method for mapping a generic model containing ligament and muscles onto the patient-specific model using the geometry of the spine we received from the segmentation tool. The method is based on automatic identification of anatomical landmarks. We defined around 40 anatomical landmarks in each vertebra of the generic model and automatically identifies those landmarks in the patient-specific vertebra, obtained from the segmentation tool. By mapping each vertebra according to these landmarks, we can rebuild the patient-specific model with the ligament and the muscles. In the next part, Pavel will explain how we perform a patient-specific analysis using Anybody software.
Okay, thank you, Samuel. So my part of the presentation is going to focus on the simulation model of the spine oracle. Just give me a second. Okay, so I will start a little bit with the background. As Izzy explained, that we had interesting conversation with Agada Medical about what makes or breaks the patient-specific case. And Agada Medical asked to help us to provide the technology that would answer this question. So we are assisting Agada Medical in developing a model for musculoskeletal modeling, using musculoskeletal modeling that will create a patient-specific musculoskeletal model, and it will quantify the behavior, the biomechanics of the patient's spine. And we set a couple of objectives. The first one was to create a highly accurate patient-specific model using the data that comes from the spine oracle. And this model should be able to simulate activities of daily living in different states, so in preoperative and postoperative states. And we should be able to do retrospective studies that should enable machine learning and other tools. And we should also be able to analyze different surgical strategies, as you said, because this is something that could eventually help surgeons to select their approach. And all of that, of course, has to be fully automated because I think it's very demanding to do the simulations manually. So here is a schematic explanation of the simulation model. So as Samuel said, Agada Medical, using spine oracle tools, generates a segmentation of the patient. It also has the information about the height and weight of the person, and so on and so forth. And they know exact surgical plan. And this is something that is being sent to the simulation model using a specifically defined protocol. And knowing this data, we start reconstructing the patient. So we take into account the geometry, we use into account soft tissues, so we calibrate for the patient, we add spinal implants, if any, and we are looking into adding functional measurements and motion capture to represent the patient even better. Once we create the patient-specific model, then we are ready to do analysis, and we look into different surgical scenarios, into preoperative situation, into postoperative outcomes, functional outcomes. We try to analyze different alternative surgical strategies. And for the movement, for the activities of daily living, we are currently looking into primary movements, and we believe that these are basis movements for more complex movements, but we are of course not limited. We can also do something else. And we use a lot of tools that we use internally in Anybody. We use AnyPy tools that allows us to automate all the simulations. We use SnakeMake that allows us to run large-scale simulations in an efficient manner. And once the simulations are done, we then send a report to the Spine Oracle, which contains various biomechanical parameters of the patients, such as kinematics, intradiscal forces, moments, facet joint forces, and loads on the spinal implants. Excuse me. And this is the model that actually allows us to do different studies. For example, one of them is, of course, being the retrospective study, where we can analyze what happened to the patient. We can compare it with the real outcome. So now I'm going to go a little bit in detail how everything works. So as I mentioned before, the very first objective is to create a very accurate representation of the patient. So for that purpose, we use the latest Anybody model that includes the thoracic spine, as you can see on the screen. Here it contains the rib cage, it contains the deformable thoracic spine. And we morph this model into the patient model using information that comes from the segmentation. We also use the patient-specific geometry to define contact pairs for the facet joints and so on. The next step is to calibrate the soft tissues. So again, here we use medical images and positions that are known and coming from Agada, and sometimes we also look into hypothetical configurations for calibration of the ligaments and the discs. And then we calibrate the patient-specific model to that positions. And if the patient has an implant, or we are looking into like a post-operative scenario, then we add implant models from the library that we have at this point. And we apply different surgical techniques such as facetectomy, ligament resection, and so on. And you can see it on the screen. And as I said, we are also looking into the adding functional measurements, for example, range of movement and different motion capture, different movements using motion capture to calibrate the patient even better. So currently, our library of the spinal implants is not very large, but it uses commonly used spinal implants that are used in the industry, such as rods, cages, intervertebral disc replacements. We implemented these spinal implant models for those implants that we know geometric dimensions and material properties. But at the same time, we are looking into adding more implants to the library, and we are looking into more sophisticated designs and producer-specific and custom and patient-specific implants as well. And then we, of course, do the simulation. So we looking at the biomechanics of the primary movements. So we're looking at the flexion, extension, lateral bending movements, and axial rotation. And that gives a good understanding of how the spine behaves using a particular surgical configuration. At the same time, we also look at the response of the passive structures and interaction of the spinal implants with the spinal column itself. And for example, one mode of simulation that we did, we applied torque at the cranial end of the spinal column, and we use the follow loads as well, similar to finite element analysis. And that basically produces some results, produces some numbers. And here is a small example. So we compute patient-specific forces. We output everything that is interesting for Agada. We look into intradiscal forces, facet joint contact forces, strains in the ligaments, forces in the ligaments, different spinal kinematics. We can also look into spinal implant loads. We look into the rod stresses. We produce interface forces. For example, if you want to analyze the pull-out forces on the screws, we can compute those as well. And of course, different compressive shear forces and so on and so forth. And last but not least, of course, we produce graphical output. So I think the spinal biomechanics is rather complicated. Sometimes it requires the graphical output to understand what is happening. And of course, we can produce video of movements in different planes, screenshots, and so on. And here, I think the simulation model is being developed using the technology that we use here in Anybody. And for example, our generic model, AMMR, is being continuously tested. And we use a variety of benchmark tests where we compare the behavior of the generic model. We compare to the previous version, so we analyze the changes that are happening in the MMR, and we are in a good control if any changes are happening. And of course, we are also comparing to the available experimental data. And this is inherently is being used in Agada as well, but at the moment we are also developing the model in such a way that it allows for verification and validation for uncertainty quantification, and of course retrospective analysis that also help us to understand how the model behaves. But I think Kobe is going to talk a little bit more about that, and I will pass the word to him.
Okay, so I will talk about the validation or verification that we're ongoing process. The validation in this case of spine surgery or any spine softwares is pretty challengeable because the simple thing that we cannot put in a live person sensors for monitoring forces and loads. So it is a challenge. So one way to do it is the kinematic validation using the Anybody software simulations and comparing to GateLab and standing flexion extension X-rays. The another way is, of course, doing force analysis validation plan to perform on cadaver studies. We haven't done it yet. It's in our plans, and it's an ongoing process. As I said, we have, as my colleagues mentioned before, we have the motions that we are simulating is the three motion of flexion extension, lateral bending left and right, axial rotation left and right. So we have 3 axes and 6 different motions. The forces that we are monitoring is the shear forces, compression forces between vertebrae, and the facet joint forces. These are the parameters that we are handling. As I said before, we can see here the simulated model and the X-ray, like measuring the geometry, lordotic angles, and any other parameters. And of course, this is one way to do it. And you can see the motion. We are getting the exact angle as the X-ray. The other way, as I mentioned, is the doing the cadaver studies with sensors and load cells. This is just an example a test set up in University of Pittsburgh. We've known many other labs that doing this cadaver studies, and we are planning to do it in the pretty next future. As I said before, one of the goals or the advantage of our abilities and software that we are doing is to doing comparison study between different configuration, surgery configuration. If, for example, the surgeon is there is a question or 2 or 3 different configuration that you want to compare, so it could be comparable and not exactly the exact force, but different configuration, what is preferred and what is less. Regarding the analysis of the stress analysis of rods and screws, it's more, let's say, more simple, because the stresses of rods, it's simple calculations of stresses. We did also finite element analysis. So in this case, it's pretty simple to simulate. This is my my part. I will move forward to the my colleague.
Thank you very much. So just before we go to the Q&A session, I would just like to thank all of the presenters for taking the time to do the presentation today. And then I would like to mention a bit about our online resources. So if you want to know more about Anybody Technology, then I will highly recommend you to go to our website, where we try to maintain a publication list of things that have been done with our software. And there's currently more than 900 publications there. And you can go and filter it by either industry, research area, or body parts, so you can find your own area and figure out what has been done already and get some inspiration. We do also have a library of webcasts there, which you can filter by industry. And I'll do my best to process this webcast and put it there as well within a couple of weeks. So you should be able to find the recording and share it with some relevant colleagues if you want to. And also you can go and find some inspiration there as well, see what has been done previously. Then last but not least, I would like to mention that we will be present at the AAOS next week, and we will have a booth there, 4857. So if you are attending and you want to meet up with us, then please feel free to send us an email. I have added the email here on the screen. And you can also just schedule a call or a meeting with us if you want to know more about Anybody Technology. And if you want to know more about Academic Medical and the Spine Oracle, then please feel free to write down the emails there to get in contact with either Kobe, Izzy, or Samuel. And with that, I would like to go to the Q&A session, and we would have a look at what questions have been coming in already. So just a second. So I think the first question is for you, Paul, and it's about how the soft tissue calibration is done with patient-specific CT data and how it is validated. I'll just turn the microphone to Paul as well.
Yeah. We are sitting close to each other, so it's easier. Yeah, that's a good question. The soft tissues, basically what happens is that the Spine Oracle operator basically defines the calibration posture, and it can be either the CT scan position, which we understand that is not necessarily the perfect calibration posture, but this is the best that the person might have at that time. But alternatively, the operator of the Spine Oracle can define a slightly different position. And for example, for the alternative surgical strategies, you can define a different movement of the spine to calibrate the spine in. And basically the system is flexible to choose different calibration postures. But it, yeah, So there is no fixed way. I mean, we are using particular approach, but we use different configurations to calibrate it in.
Thank you very much. So for the next question is for you, Izzy. So we have one attendee saying, thank you very much for an interesting webinar. And this seems like a very exciting technology, and it sounds like it's still a bit under development. So could you talk a bit about what is the future for the spine oracle and when you expect it to be on the market?
Thank you for that, Chris, and thank you to the attendee for that question. Chris, I've got some other slides that can help really answer that. If we can allow me to present again,
Yeah,
I can show where we are today and some of the data that we're generating.
Just give me 1 second.
So you're the presenter now?
Yeah, so we see your screen now, Izzy. We see your browser.
All right, there we go. Okay, so this is where we are today with the collaboration of Agada and Anybody Technologies. We do have 3 components to the Spine Oracle that are functional at this point. We do have our spine segmentation algorithm, which is a working prototype complete. And in fact, we are already commercial with that. We do have other commercial entities using our segmentation module to create segmentation models for their respective technologies within the robotics and within the imaging field. The lumbar spine simulation module, which is our module to look at the forces, analyze the forces above and below 1, 2, or 3 level lumbar fusions and disc replacements. The working prototype's complete right now. We are in progress with our validation and verification of that, and we anticipate a commercial launch of that Q3, Q4 of 2024. And again, with the wonderful help of Anybody Technologies, the thoracic spine simulation module is now a functional prototype that we are further developing. But what I do want to share is some of the data that we're able to generate and show you the overwhelming nature of the data, but potentially the real benefit of the data. So this is one case. This is an L4-5 degenerative spondylolisthesis where the L4 bone is slipped on the L5 bone, causing all sorts of biomechanical anomalies above and below. We go ahead and reduce it, meaning realign the spine, fuse it in that place. But we do that with multiple different tools, different cages, 5-degree, 10-degree, 15-degree cages. And here I'm presenting just the disc shear forces at the levels above and below the 4-5 fusion at L3-4 and at L5-S1. And you can clearly see that if we use the 5-degree cage, we are amplifying the shear forces at the L3-4 level and at the L5-S1 level. We go to the 10-degree cage, we're kind of normalizing it, but the 15-degree cage gives us the exact match to what the native state is. Now, what we don't know is that what we should be aiming for? And that's where the future, where the ability to generate this data and put in predictive analytics with this and the machine learning with this, we'll be able to say, this is what we should aim for, and therefore we should use a 10-degree cage, a 5-degree cage. But we do have to balance that with this. So what I showed you before was the disc shear forces. This is the same case now, looking at the facet joint forces. And you can see that the numbers are a little different. Now, intuitively, as surgeons, we've known this for a while. As spine biomechanic experts, those in the audience have known this already. You do one thing to the disc, you're going to alter what's going to happen at the facet joints, but we haven't been able to quantify it. Now we are able to quantify it. So again, looking pre-op 5-degree cage, 10-degree, 15-degree cage, you can see under these circumstances, using the 5-degree cage does increase the facet joint forces at the 3-4 level. But at the L5-S1 level, it neutralizes the facet joint forces. So here we are with a dilemma. What's the cage that we need to use? What's the right balance that we need to use? And the only way we're going to know that is with the collection of all this data and using thousands or hundreds of thousands of cases to figure that out. Now, when you say the number hundreds of thousands, you think, it's impossible. We'll never be able to do that. But in fact, we are. We have access to 2 very large databases right now, one with over 350,000 spinal surgeries done in the United States, including patient-reported outcome measures, as well as their radiographic data. So in a retrospective fashion, we can start training the spine oracle algorithms, validating them as we start collecting this data prospectively. So that's what I just wanted to bring to light. And again, just to summarize, this is how we are doing things by taking the imaging, the anthropometric data, and comparing dynamically different surgical strategies. So I hope that answered the question.
Thank you very much, Izzy. So I'll just make myself the presenter again so anybody can see the contact information. There we go. So the next question is for you, Paul, and it's regarding the musculoskeletal modeling. So are the passive properties of the intervertebral disc accounted for, and what degrees of freedom are the joints modeled with?
Yeah, so we basically use almost a forward dynamics approach where the discs are elastic elements and there is no kinematic joint between them. So it's a free floating joint with elastic properties and passive joint contacts in between. So basically we are running like almost like a finite element simulation. So we call it force-dependent kinematic mode of solving for kinematics. And yeah, basically this allows us to also simulate for different elastic and quite stiff elements as well, so such as cages and so on. So I'm trying to answer another question at the same time. Yes.
Thank you very much. So we have another question about validation, and this one is for you, Kobe. So an attendee is writing that validation is indeed difficult. So how are you planning to validate the predictions made for individual patients to ensure that the software is safe in advising clinical decisions in surgical planning?
Well, thank you for the question. As I mentioned before, we are validating it using cadaver studies and finite element studies on specific cases. So this is our main target within the next time. This is the method. As Izzy mentioned, we have a retrospective studies that you can do on statistical data on hundreds of patients. So this should be good and to validate our software.
Thank you very much. So now I'll hand over the word to you again, Izzy. We have another question for you. So this is about what you would have done differently if you knew the rods in the case you presented was likely to fail. So the simulation suggested that they were heavily overloaded, and in what way could the Spine Oracle platform help you re-evaluate the surgical plan?
Again, thank you to the attendee for that question. Very pertinent question. If you look at the last 15 years of spine surgery, we became absolutely tunnel visioned about alignment and lordosis. And we went from trying to achieve the optimal lordosis for, say, a 20-year-old individual. But what we didn't appreciate at that point in time is that your lordosis is different when you're sitting and standing, and the required lordosis that you need as you age also changes. So over the years, we evolved to now what we're calling age-specific alignment criteria. Now, I've always maintained that it's not age-specific, it's function-specific. I see 40-year-old patients that function as if they're 80 and effectively only go from the bedroom to the kitchen. And I see 80-year-old patients that function like they're 40 who are still out skiing and golfing and riding their bikes. So each one of those individuals is going to need a different lordosis. What I did in that case is I fell into that trap of thinking, this person needs this much lordosis. But it was pretty clear 6 months later that I gave her too much lordosis. And what would have probably been the easiest solution for her was build a patient-specific rod with less lordosis on the basis of her functional requirements. Now, there's another evolution in spine surgery right now, and I must admit, I don't agree, sympathize with it. I don't subscribe to it as much as my colleagues do, but everyone seems to think that the answer is more metal, heavy metal, add a third rod, add a fourth rod. No, the answer is not more metal adding rods. The answer is assessing the most appropriate biomechanics and neutralizing those forces. So yeah, in her, I could have added a third rod or a fourth rod, but over time, even that third or fourth rod would have eventually broken. So this is the information that we will be able to generate using the Spine Oracle and the various solutions. And if I knew those solutions ahead of time, I could look at the patient and say, okay, this is an 80-year-old that wants to play golf and tennis, needs this much. Or this is a 50-year-old that only sits in bed all day, they need that much lordosis, alignment, rod size. I think I answered the question.
Perfect, very much. So I will keep your microphone on, Isis, because there's another one for you. Another attendee who would like to thank you for a great presentation. And he's writing that this concept could be transformative to patient treatment. Do you have any concerns over liability if you were to take advice from a software?
I'm presuming that this attendee is a medical care practitioner. And if he or she is, we're always concerned about the medical liability associated with this. Yeah, every day I'm concerned. When I go to bed at night, I'm concerned. When I wake up in the morning, I'm concerned about every operation that I'm about to do. Now, the philosophy that I'm approaching is, yes, this is going to be revolutionary. The premise is that this is a decision support software. But as we gain experience with this, as the software learns and becomes more accurate, we are going to be able to, with confidence, say, this surgical solution has a 92% chance of success, a 98% chance of success. I doubt that it's ever going to be a 100% chance of success. But if I've done as a surgeon everything I possibly can to preoperatively plan, to explain to the patient and show the patient that this is what my opinion is, this is what the software verifies, and then I execute according to that plan, I've done everything I can to ensure the outcome. And if the software, and I feel that we're going to have a 98% success rate, and unfortunately that patient ends up in the 2% with a less than desirable outcome, I think I'm protected to a certain extent. I haven't left anything behind. I haven't ignored any factors. I've done everything, I've used every tool in my power to ensure that outcome. So it is a concern, but this is one way to mitigate that concern. Chris, are there other questions? Pavel, I think you're muted.
Oh, sorry. So we were saying that we're really getting a lot of questions and we are running out of time. So I think we will take one more question. But if you have anything you would like to ask us, then please feel free to send in your questions now and we will answer them by email. But for the very last question, so we have a more technical one for you, Paul, and it's about how you model the facet joints.
Yeah, as I said, we are using the force-dependent kinematics approach, and we know the information about the facet joint geometry, so we can take it into account. So we have contact pairs defined for the simulation, and we have the facet joint capsule also included, and basically we use an honest approach where we do the contact analysis of the facet joints, and we also look if ligaments are stretching, so the capsule is stretching. Then we also have those forces as well. So yeah, so we do take into account the facet joints. Yeah.
Perfect. Thank you very much, and thank you very much to all of you for the presentation. I will do my best to process the recording as soon as possible, and we will put it out on our website, so it should be available there within a couple of weeks and hopefully even faster. With that said, I would like to thank all of the attendees for listening in, and I hope to see you again for another webcast in the future. Thank you.
Thank you, Chris and Pavel, Kobe, Shmulik. It's an exciting time, and I'm just honored to have such expertise around me to bring this technology to our patients' benefit.
Thank you.
Thank you.
Have a good day, everybody.